Imagine you have a population of 50 rabbits, and from a study done in the area you know that each rabbit produces on average 2 young per year, and from one year to the next half of the original population dies. How many rabbits will there be a year from now? Simple enough, right? 50 rabbits, 2 young each, 100 new young. Half of the 50 die, 25 left. In total, 125 rabbits. With this, we can predict how the population will behave. Each year, it multiplies by 2.5. From 125, we'd go to a little over 300, and then to almost 800. If we follow this trend over time, the population takes off with exponential growth. But there is something that doesn't quite add up. At the start, we said that each rabbit produces 2 young. But even the rabbits that were just born that generation are going to produce young? Obviously not. First, they need to develop and reach sexual maturity. We've been wrongly assuming that all of them would reproduce. That means not all 50 rabbits at the start count the same. So 50 rabbits doesn't tell us enough. We need to know who those 50 are. That is, we need to know the population's age structure. Let's go back to our 50 rabbits. Now we know that we're missing information to figure out what happens to this population over time. So let's take a closer look. And it turns out that this rabbit species lives only 2 years. During the first is a juvenile that doesn't reproduce, and during the second year it does. So there are only 2 kinds of rabbits that behave differently. To start, let's imagine the simplest possible case, a population of 50 rabbits where all of them are newborn juveniles, no adults yet. How do we write this down? The most natural way, 2 numbers, 50 young, 0 adults. Now, we don't just have how many rabbits there are, but how they're distributed by age. This, which is nothing more than an ordered list of numbers, where the order matters, is called a vector. But for now, we're not gonna pay much attention to that label. It's just a way of saying these numbers go together and the order matters. Because if we swap them around, we'd be talking about a completely different population, with 0 juveniles and 50 adults. So this is our starting point, not 50 rabbits, but 50 young and 0 adults. We'll call this the state of our population. And now we go back to the question from the start. If this is the state today, what is the state a year from now? To know what the population will look like a year from now, we need to look again at the rules we know. But this time taking the differences between ages into account. The easiest way is to forget about the 50 rabbits for a moment and see what happens when I have just 1 young. What does this young leave behind for the next year? First, does it have offspring? No, it's a young. It doesn't reproduce yet. And itself, is it still alive next year? The study we saw told us that half survive. But half of what? We know the adults don't survive, so does that figure take all ages into account? Well, going back to the study, we see that the number was for first-year rabbits, that is, the young. So on average, each juvenile leaves behind half an adult. I know half an adult sounds strange. There is no such thing as half rabbit. But we are not talking about one real young. We're talking what an average young contributes. Out of every 2 juveniles, on average, 1 makes it to adult. For a single one, half. That's all a juvenile contributes to the following year. 1 column, 2 numbers, again another vector. Now, what happens when I have 1 adult? The same 2 questions. Does it have offspring? Yes, we know this from the study. On average, 2 young. Is it still alive next year? No. During the second year, they reproduce and die. These are not the rabbits you're used to in real life. This made-up species reproduces once, and that reproduction costs its life. So the adult itself doesn't go into the next year, just its young. But even if they did survive, it doesn't really matter, because this age class is defined by being between 1 year and 2 years old. So if they survived for the next year, that means they wouldn't be in this class. They would be in another class that would be defined from 2 years old to 3 years old. But we don't need to think about that other hypothetical class because we know that they don't survive to age 3. With this, we've got everything. Notice that these two columns contain everything that we need to know. The one on the left says what a juvenile produces or contributes for next year. The one on the right, what an adult contributes. This table, which is nothing more than two lists of numbers, is called a matrix. And in this specific case we're using it for, it's called a Leslie matrix. Just like before, for those of you who don't get along with math, don't fixate on this being a matrix, and don't try to remember its properties or operations. For now, the only thing that we need to know is that it's where we've placed, in order, what each kind of rabbit contributes. And again, the order matters. The top row is the young that arrive, 0 from the juveniles and 2 from births by the adults. And in the bottom row, the adults that arrive, half a rabbit from the juveniles that survive and 0 from the adults. Those two numbers that came out 0, top left and bottom right, aren't just empty. Each one says something. A young isn't born from another young, and an adult doesn't survive. The matrix does not only store what happens, it also stores in its zeros what cannot happen. So we've got the two pieces now. Today's state, 50 young, 0 adults, and the rules, so we can apply them. And doing that by hand is very simple and intuitive. We know how much a rabbit of each kind produces. We just have to multiply it by how many we have. Let's start with the young. We know that one young contributes 0 new young and half an adult. But we don't have one young. We have 50. So what all our juveniles contribute is the same thing 50 times. 50 times 0 young, 0 young. 50 times half an adult, 25 adults. Our 50 young, altogether, leave no new young, but they do turn into 25 adults. Now, to this, we have to add what the adults produce. We know what each one contributes, but we have 0 adults, so they contribute nothing this time. Now we simply add what the young produce to what the adults produce, and we get 0 young plus 0 young, 0, and 25 adults, plus 0 adults, 25 adults. And there's the state a year from now, 0 young and 25 adults. Again, we have a vector. But this one describes the state of the population a year from now. Notice what we just did. We took each class of rabbit, multiplied what one contributes by how many we have, and then added up the contributions from each class. That's it. And this is basically multiplying the matrix by the vector. But it's not a new rule you have to learn. It's just exactly the calculation we just did with the rabbits, and it's very intuitive. And now that we have next year's state, we can do the same thing again, starting from 0 young and 25 adults. 25 adults, 2 young each, 50 young, and we don't have any juveniles yet, so 0 adults. So for the third year, 50 young and 0 adults. And if you notice, that is exactly where we started from. That is the state that we had at the beginning. This population is not growing, it's going in circles. 1 year all juveniles, the next year all adults. And back to the start. It oscillates, and on top of that, without growing. So this is very different from what we estimated at the beginning. This population, with these particular rules, doesn't grow. And all of this difference came from one single thing. We stopped treating the rabbits as one indistinct pile and started counting who is who. This doesn't mean every population actually stalls. It happens to this one because each adult leaves 2 young, but of those 2, only one makes it to adult. So virtually an adult produces in the long run just a single adult that replaces it. So the population cannot grow in the long term. It just keeps on replacing itself. And the same thing, that is this oscillation that we've been seeing, happens even if we start from a different split, like 2030. If we run the same calculation, we would end up getting, again, the same number that we started from, and this goes on forever just like before. It stays in a loop. But if instead of changing the initial state of the population, we change the matrix, we're gonna get a different result. Let's say, for example, that we have another population that instead of producing 2 offsprings per adult, it produces 3.5, and instead of half of the juveniles surviving, now it's 80%. In this case, as you can see, the population is growing. In fact, it's growing quite fast. And this time it resembles what we saw at the beginning: exponential growth. But weirdly enough, it still oscillates. Even though it grows, every year it oscillates between being dominated by adults or being dominated by juveniles. It doesn't reach an equilibrium. Thus far, we've been only working with 2 age classes, but the same things we've learned apply to more. Let's now imagine a new species of rabbit that lives up to 3 years. Now, just like before, we'll have to keep track of what an average juvenile produces, what an average adult produces, and now what an average old adult produces as well. For this example, we'll say that the adults produce 2 juveniles, but the old adults are less fertile and produce only 1.5 juveniles. The survival rates will say that they are the same from juveniles to adults and from adults to old adults. But if we plot this population over time, we'll notice something strange. At first, it looks like what we're used to, jumping between being dominated by one age class to another. But over time, it stops oscillating, and the population gets distributed by class in stable proportions, almost by magic. This is very different from what we were seeing before, where the populations of every example we saw oscillated to infinity. And we can better visualize this pattern if we plot the percentages of individuals in each class, instead of the number of individuals. In fact, if we look at the graph of the left population, we can see that even though the total population was growing, the oscillation in the proportions of age classes was always the same, meaning that the population is not going to get stable proportions, it's gonna keep oscillating like it has been. But how is that possible? How can the same operation give 2 completely different behaviors? Is it just because of the extra age class, or is there something deeper going on? If we try different starting states and see where each one lands, we can see that it makes no difference. A population's fate doesn't depend on where it starts. The only thing that ever changed the outcome was the matrix. Whether a population grew, oscillated, or settled into a constant age structure, everything was decided by the matrix. But so far, the only way we know to see where a population is headed is the slow way. Take this state, apply the matrix, and repeat. Year after year, one step at a time. And that's fine for 2 classes over a few years, but what if we had 10 age classes? Or what if we wanted to know not next year, but in 100 years from now? Would we really have to go through all the 100 steps one by one? There has to be a better way, some way to look at the matrix and just read off the population's destiny, whether it's gonna grow, oscillate, or stabilize. But we'll leave that for the next video.